Now this is the robotics arm model which I have developed a few months ago, and I have performed its motion analysis. This motion analysis will help us calculate the amount of torque and the power required by this robotics arm to perform its operation. More specifically, we will calculate the power and the torque required by the motor which is sitting here. This is the arm motor to carry the arm, the jaws and the weight. So how we're going to achieve is that we will lift this weight with the help of the jaw and then lift the arm with the help of the motor. And then we will plot the graph of torque versus time. And the graph will let us know how much torque that the motor should have in order to carry these three things, because the arm and the jaws have their own weight. How I will conduct this motion analysis is first I will go through the process of how I have set up the motion analysis, how I have set up all these keys and how I have set up all these things. And then I will let you know how I have plotted the graph between torque and time, and then we will validate these values which we have obtained from SolidWorks against hand calculations. Now the material I have assigned to this robotics arm is polyether ether ketone PEEK material. Why I have assigned is because it is as strong as metal but it is lighter in weight, because we need to keep the self weight of the robotics arm as minimum as possible, because it needs to carry the external weights like this aluminum block. By the way, this aluminum block is 0.5 kg and it is aluminum 1060 alloy. This information of 0.5 kg will help us in hand calculations. Now here I will run the motion analysis to give you an idea of what I am talking about. I'll just give it a play. And as you can see, when the robotics arm reaches above the platform 1, it picks up the load and then it starts to rotate again. And then as it reaches the platform 2, it drops the load. Now if I pause it here and I go back to the graph which I have plotted, as you can see, if I move the slider on the timeline, it will move the slider, this red color slider on the graph as well. And you can see that after around 3.8 seconds, as at 3.8 second, the robotics arm has picked up the load. That's why the torque has increased so much. Now I will discuss this graph in detail at the end of this video. For right now, let's jump straight into how I have set up the motion analysis. One thing I want to make clear before we start is that here we have three options: animation, basic motion, and motion analysis. In the motion analysis tab, this is the real world scenario, and everything you need in the real world, you need to set it up here, because that's how you're gonna get the accurate results. Now, what do I mean by that is, in real world, I will show you with an example. So what do I mean by that? Because in real world, when something falls on the floor, it comes into contact with it and it stops at the floor, just like this. But SolidWorks does not know that. Whenever something comes into contact in SolidWorks, it just passes through it, just like this ball. So we need to set something up so that the SolidWorks know that these two things, when they come into contact with each other, they must stop. Now, how are we going to set this up? We will go into the motion study and we will make sure that we are in the motion analysis option. And now I have already set up these things, but I will delete them and I will show it from scratch. Now, if I play the animation, I want the ball to fall on the ground. So for that, as I have already told you, that we need to set up real world scenarios, and in real world we have gravity, but SolidWorks don't know what is gravity, so we need to set this up. If I go to the uh, gravity option, now it says I want gravity, but it is saying that it will act in the Z direction, and Z direction is, as you can see here, and it is also showing you another arrow which will point to the direction of gravity. But we want the gravity in the negative Z direction because positive Z is upward. So we'll select Y and it will automatically shift you in the negative Z direction. By the way, if you want to in it in the positive Z direction, you can just flip it. But we want in the negative Z direction and we want this value. Now we need the actual value to be 9.8 meter per second because that's a real world value. But as I have set up the units in millimeter, that's why it is showing 9806.65 millimeter per second square. So I have set up the gravity. Now when I will play the motion analysis, what you will see is that the ball will not come in contact with the plate. It will pass through the plate because SolidWorks does not know when two things come into contact. So we need to set this up as well. So first I will play the motion analysis, and as you can see, the ball has passed through the plate instead of stopping at the contact. So we need to set up something else so that the ball knows when it comes into contact with the plate. So we'll come at the contact and we will select both of the things we want. The contact, this is the ball. If I move back the animation, just give me a second. Now if I go to the contact again and select the ball, this is the ball, and the plate, this is the ground. Now we can set any material type contact we want. I want steel dry. Now I have set up the contact. Now the SolidWorks knows that these things, whenever they come close to each other, they must make a contact. Now if I run the calculation, you will observe that the ball will stop at the contact. As you can see, the ball has stopped at the contact. So that's what I mean when I say that we need to set up everything that's in the real world. One thing you might have observed that only the ball is falling down and not the plate. The reason is that I have made the plate fixed. So whatever thing you have fixed, it's not gonna move. So only the gravitational force is only acting on the ball. If I made the plate float, both of these things are gonna fall down. As you can see, both of them are falling down. But we don't want that. We want to demonstrate an example when two things come into contact. So we need to fix the plate. Now no gravitational force will act on the plate. Only the gravitational force will act on the ball. As you can see, the ball is falling down. Now I will go back to my robotics arm example. Now I will go to the motion analysis of the robotics arm, and you can see that I have set up the gravity here in the negative y direction, and I have set up three contacts. The first contact is between platform 1 and the aluminum, and you can see that the platform 1 is fixed. The platform 2 is also fixed. So the gravitational force will have no effect on these platforms. Why I have made this contact is because this weight is not fixed. And if it's not fixed, the gravitational force will have an effect on it and the weight is going to pass through the platform. And we don't want that. We want the weight to be standing on the platform. That's why we have made a contact between this platform and the weight. And the second contact is between the weight and the platform too. Now, why I have set this up is because when the weight is going to fall on the platform too, we don't want it to pass through the platform. That's why I've set this contact up. And the third contact is between the jaws and the weight because as you can see, whenever the jaw is going to come close to the weight, it needs to grab the weight. And in order to grab the weight, there needs to be contact because if there is no contact here, the jaws are going to simply pass through this weight. Now to keep the motion analysis simple, I have only added three motors. I will go back to the model tab. The first motor is at the base, which is to rotate the entire body of the robotics arm. The second motor is at the arm to lift the arm and the jaws. The third motor is at the jaws. If I select the top face of this mini cylinder and if I move it downward, you can see that the jaws are opening. And if I move this upward, the jaws will close. So we'll set up the linear actuator here. So linear actuator is basically something that converts the rotational motion into linear motion. Now I will go back to the motion study tab and I will tell you how I have exactly set the motors up. I will select the motors option here. Now you can notice that there are two types of motion, rotary motion and linear motion. Now we want the rotary motion at the base. So I will select this option and now we need to pick a place where we want to set up the motor. I want to set this motor at the base, so I will select this face and notice you can see the arrow. This arrow is pointing the direction of rotation of the motion. We can flip it by selecting this option, but in this case the direction of rotation does not matter. Now there are three options here in which we can give input to the motor. First is displacement, velocity and acceleration. We will give the input in terms of displacement. We will give some degree value to the motor in order to rotate the motor. That's how we're going to set up the base and the arm motor. And for the linear actuator, I will go back and I will select the motor option again. And this time I will pick up linear motor actuator. Now again I will be selecting the face. I will select the top face of this mini cylinder. And this is the direction in which it's going to move. Again, I'm going to select the servo motor because I want controlled motion. And again, we are going to control the motor with displacement values. That's how we're going to set up the motor. As you can see, the motors have already been set up here. Now, everything we need to set up in the motion analysis tab has already been done. Now we need to go to the event-based motion view. If I click it, now this is the view where I have set up the keys for motion analysis. It looks a bit difficult, but actually it is not. The first column here is representing the names of the tasks. Now each task has a certain type of motion of the motor associated to it. Now this whole bar is 10 seconds long, starting from 0 seconds to 10 seconds. Now the 10 second is not visible here, but it will be visible in the timeline view, as you can see here. Now if I go back to the event-based motion view, now in this section you can see different sized orange color bars. And these bars are associated to their respective tasks. For example, this first bar is for task 1, the second one is for task 5, this one is for task 2, and so on. The keys which you are seeing in this timeline view are because of these orange bars. And these orange bars are generated because of the settings we made in this event-based motion view. Now the next column is trigger. Now what this means is that whatever the change in motion we're going to set up in this action section, how we want to trigger this change in motion. In this case, I have set it to time. So I want to trigger this motion by time. Notice I have set the time to 1 second. It means that this change in motion is going to start at the first second. And you can see that the orange bar for the task 1 is starting at the first second. And if we just skip these three sections, these three columns, and we jump to the duration, we have set the duration to 2 seconds. So it's going to start at the first second and it's going to end 2 seconds later at the third second. So this is what I mean by this column trigger. The next column is the features column. Here we will select what we want to move. So I have selected the base motor here. This rotary motor is the base motor. The next column is value. As we have selected the motor, so we want to rotate the motor. So we need to assign some value in terms of degree so that we can move the motor. So I have assigned a value of minus 15.47 degrees. Now as I am at the 0 second, if I just zoom out, now this position of this base motor is the starting position. It means that it is at the 0 degree. And as I have set this task from the first second to the third second, and the value is minus 15.47 degrees. So what it's going to do is at the first second, the value of the degrees will be 0 and the value will gradually change until it reaches to negative 15.47 at the third second. And by this time, the third second, the jaw will be at the top of the aluminum block. Now if I move the slider and if I stop at the first second, notice there is no motion here because we didn't set up any motion here. We set up the motion at this section. So if I go from the first second to the third second, you can see that the jaws are now at the top of the aluminum block. So now we need the jaws to pick up the aluminum block. So we need the jaws to close. So in the task 2 here, in the features section, I have selected the linear actuator. And the linear actuator is the one I have set up here in this mini solid cylinder. And I have said that when this cylinder will move upward, the jaws will close. So we need to close the jaws now. So now I have given the value of 4.08 millimeter and we are triggering it at the third second. So at the third second, when the jaws are at the top of the aluminum block, we want the jaws to close. So we have set up the third second and the total duration is 1 second. So at the fourth second, the jaws will close, meaning this cylinder will move upwards by 4.08 millimeter. So now if I jump to the fourth second, as you can see, the jaws are now closed and they have grabbed the aluminum weight. Now since this weight is placed down inside the platform 1, so we need to lift the weight up. So we will lift the arm with the help of the arm motor. Now the next task is the arm motor. So we have selected the arm motor here and we have triggered it at the fourth second. And at the fourth second, the jaws have now grabbed the aluminum weight, so we can safely lift the arm up. So at the fourth second, we are triggering this animation, and its duration is 1 second. And the value we have given is 15 degrees. So when I will jump to the fifth second, the arm motor has lifted the arm by 15 degrees. Now we want to bring the aluminum weight above the platform 2 because we want to drop it at the platform 2. So the next task we have assigned again is of the base motor. Since this motion is very long, so I have given it 3 seconds of duration. And notice the value is 90 degrees. So when I will reach the 8th second, the base motor has undergone rotation by 90 degrees. And you can see that the weight has now arrived above the platform 2. And since this height is very high, and we don't want something to fall from very high height, so we need to lower the arm with the help of the arm motor. So now we will go negative 12 degrees to lower the arm. So the next task is minus 12 degrees, and it's triggering at the 8th second, and its duration is 1 second. So at the 9th second, you will see that the weight will be closer to the platform 2. As you can see, the weight is now at the reasonable height. Now we can safely open the jaws and release the weight. So the next task is linear actuator again, and it's minus 4 millimeter value, and it's triggering at the 9th second, and by the time I reach the 10th second, the jaws will be open and the aluminium block will be on the platform 2, as you can see. After all of the keys have been set up, just simply hit the calculate button. Now it will start to calculate the motion study. Now this is not the basic animation, this is the real world motion. Because if you plot the graphs now, it will give you the actual value of the power and the torque required by this motor to perform these operations. Now since I have already calculated the motion study, so I will pause it here. Let's plot the graph between torque and time. Click on the results and plots option, and in the feature manager design tree, in the first drop down menu, select forces. In the second, select motor torque because we want to calculate the motor torque. I will select magnitude here. In this section, we need to select the motor whose torque we want to calculate. So I will select the arm motor in the motion analysis tab. As you can see, the arm motor has been selected. Now hit the OK button. But as in this file, I have already plotted the graph, so I will hit the cancel button. But instead, I will go to the motion analysis section, and in the bottom, there is a results folder. This folder contains all of the graphs that you have plotted. Now ignore all of these graphs and just focus on the first one. Right click and select show plot. Now this graph seems a little bit weird because it shows a lot of zigzag lines. I don't really know why it is showing these zigzag lines. But if we avoid these unnecessary zigzag lines and instead focus on the main lines, I will use the pen tool to draw the main lines. If we focus only on these main lines, these lines. If we focus on these main lines, the lines which I've drawn with my cursor, these are the values that we are looking for. These are the actual values of the torque that this motor requires to perform the pick and drop operation. So I'll just hide the pen tool. And notice when I move the slider on the graph, it updates the SolidWorks graphics view in real time. This is the SolidWorks graphics view. So when I move the slider, it updates the SolidWorks graphic view in real time. Now in the beginning, the robotics arm has not picked up any load. So you might be expecting that the torque should be 0 from the 0th to the 3.8 second, but it is not. It is 1.2 Newton meter. It is because the jaw and the arm of this robotics arm has its own weight, and that weight is creating the torque at this motor. So both the arm and the jaw are contributing the torque at the arm motor. Now this torque remains constant until the 3.8 second, because from the beginning to the 3.8 second, the load remains constant. At the fourth second, the robotics arm has picked up the load. And now, in addition to the jaw and the arm, the aluminium weight is also contributing the torque at the arm. That is why the torque required by the base motor has now increased to 3 Newton meter at the fourth second. Before moving any forward in the graph, as you know that torque is load times distance, and we are calculating the torque at this point. Let's say the distance between the weight of the aluminium and the point where we are calculating the torque is R. Now when we will reach the fifth second in the graph, the robotics arm will pick up the load. Let's say at the fifth second, the arm has reached this position. So now the load is acting at this point, which means the distance R has now increased. So it means that the torque will now increase. And this is what the graph is exactly showing. From the fourth second to the fifth second, this angle is increasing gradually. That's why the torque is rising. Now, the increase in angle is essentially increasing the distance. That's why the torque is increasing. I will hide the pen tool and see if I jump to the fifth second, the robotics arm will pick up the load. You can see. So the torque has now increased from 3 Newton meter to 3.6 Newton meter. This torque will remain constant from the fifth second to the eighth second because in this time only the base motor is working and not the arm motor. And as we lower the load from the 8th second to the 9th second, the distance the distance between these 2 points decreases. That's why the torque has now decreased. And as we release the load from the 9th to the 10th second, the torque returns back to its original value.
Now comes the hand calculation part to verify these results. But before the hand calculations, we need to know few things. First, we need to know the length of this arm. I will hide this shoulder. I will right click and select hide component. Then I will hide the motor which is sitting here. So we need the distance between the center of this circle and this point. So to get the center of this circle, I will right click on this circle and select sketch. I will click on convert entities. Now I have the center of the circle. I will hit enter. Now I will go in the evaluate section, and in that section I will select the measure tool. I will just zoom out. I will select the center of the circle and the end point of the arm. As you can see, the distance is 0.51 meter, and in hand calculations I have taken the distance of 0.5 meter, and this distance is the total length of the arm. I will first go into the features manager design tree, and I will unhide the shoulder motor and the shoulder. The next important thing is the mass of this arm and the jaw. So I will select the mass properties. Okay. First I need to go into the model section. So I'll select the model section. Now I'll select the mass properties. Right click here and select clear selections. Now here we will select the arm. So we need to select all of the portions of the arm. So we'll select all of the 4 sections. And here you can see the mass of the arm. The mass of this arm is 0.09 kg. Right click here and select clear selections again. Now let's see the mass of the jaws. So I'll again select all of the sections of the jaw. So you can see the mass of the jaw, which is 0.29 kilograms. Right click here and select clear selections again. So I will find an empty space and I will click right. I will right click and select clear selections. Now let's select the aluminum block. If I click on the aluminum block, you can see the weight of the aluminum block is 0.51 kg. Now if I hit the close button and go back to the motion analysis and display the torque versus time graph again, I have verified the results using hand calculations for 3 points. The first point is anywhere on this line. The second point is 3.8 second, where the torque is 2.9 Newton meter. And the third point is the fifth second, where the torque is 3.6 Newton meter. So these 3 points are our 3 cases. The first case is where the robotics arm has not picked up the load. The second case, at the 3.8 second, the robotics arm has just picked up the load. So this load is also now adding torque at this arm motor. And at the fifth second, the robotics arm has lifted up the load. I have verified the values of the torque at these 3 points with hand calculations. So first, let's make the free body diagram so that when we move on to the pen and paper, it will be easy for us to understand. I will open the pen tool. So this is our base. This point is our base. And this is the arm. We'll go back. I'll draw the arm again. This is the arm and its length is 0.51 meter, which we have approximated to 0.5 meter. And the weight of the arm is 0.09 kg. Now we need to decide where this whole weight will lie. So in my calculation, I've approximated it to 60% of the arm length. So I have approximated that the whole weight is lying at 60% of the arm's length at this point. So here the 0.09 kg mass will apply. And here the mass of the jaw is acting, which is 0.29 kg. And for the aluminum block, it is 0.51 kg. Another important thing we need is the angle between the shoulder and the arm. So I will just remove all of these things. I will empty the screen. I'll select the pen tool again. So we need the angle between the arm and the shoulder. So why we need the angle is because a torque is load times distance, and the distance is horizontal distance. So when our load of 0.09, when our mass of 0.09 kg is acting here, we need the horizontal distance, not the inclined distance. So in order to resolve this inclined arm into the horizontal arm, we need to know the angle between the arm and the shoulder. Similarly, the load of the jaw and the aluminum is acting here, so we need the horizontal distance for this point as well. So for this, I will hide the pen tool. Now to get the angle, I have drawn the sketch. I'll right click on the sketch 2 and I will show it. Now you can see two lines on the graphics view. The first line is at the middle of the shoulder and the second line is at the middle of the arm. So it will give us the accurate angle. Now at this point, the robotics arm has not lifted up the load. So at this point, if I click on the sketch, you can see the angle is 45 degree. And this is the angle when the robotics arm has not lifted up the load. But after the 5th second, the robotics arm has lifted up the load. So the angle between the shoulder and the arm has now changed. So if I just press Ctrl B to update the system, it will automatically update the angle between the shoulder and the arm. Now if I click on the sketch 2 now, you can see the angle between the shoulder and the arm has changed to 60 degree. So the 45 degree angle is the angle we're going to use in the first and the second case. And in the third case, we're going to use the angle 60 degrees. So let's focus on the case 1. So we need to verify whether the hand calculations are going to give us the same results that this graph is giving us. The graph is giving us 1.2 Newton meter. So we're going to verify this result with the hand calculations. So I will open my hand calculations. So this is the case 1. Let me open the pen tool. Now this is the free body diagram which I just drew on the SolidWorks. You can see the mass of the jaws and the mass of the arm, and it is acting at 60% of the arm's length. And the angle in the first case is 45 degrees. And the torque is equal to load times distance, and load is equal to mass times gravity. This is the value of gravity. So I will quickly remove all of these things. Let me just go back upwards. I'll select the pen tool again. So we need the horizontal distance between these 2 points, let's say A and B, and the horizontal distance between these 2 points, let's say C and D. First, I will calculate the distance CD, because this is straightforward. The whole arm length is 0.5 meter. If we resolve this 0.5 meter on the horizontal axis, it will be 0.5 times sine 45 degree. So the distance between the point C and D is 0.353 meters. So we will pick this value and we will multiply it with 60% to get the distance between A and B. And here is the distance between A and B. So I've just multiplied 0.5 times sine 45 with 60%. And the distance between A and B is 0.212 meter. So the mass 0.29 kg is acting at 0.353 meters distance to this point. And the mass 0.09 kg is acting at 0.212 meter distance from this point. Now let's go down. In the case 1, only 2 torques are acting at this point. The first torque is because of the mass 0.29 kg and the second torque is because of this mass. So I have added both of the torques together and I have put the values in and got the result of 1.19 Newton meter. And the value we obtained on the graph was 1.2 Newton meter. And they both are pretty close. If we approximate this value, it will be equal to 1.2 Newton meter, which is what the graph is showing us. Now I will move to the case 2. So this is the case 2, which is still at the angle 45 degrees. But now the robotics arm has picked up the load. So now this aluminium load is also creating a torque at this point. So we will have 3 torques now. Now since the angle is 45 degrees, so this whole value will be from the case 1. As you can see the value which we obtained in the case 1. The only addition is of the aluminium torque. 0.5 kg is the mass of aluminium, 9.81 is the gravity value, and 0.353 is the distance between the point C and D. And the torque we are obtaining after the addition is 2.922. And this value is equal to the value we are obtaining from the graph. The value we are obtaining from the graph is 2.9 Newton meter. You can see at the 3.8 second, the value is 2.9 Newton meter. Now if I go back to the case 2, you can see that I have also performed the power calculations. But let's not focus on this section at this point because I have not shown the power graph. In the end, I will show the power graph and I will come back to these calculations again. So I will open the third case. And you can see at this point, the angle has now changed to 60 degrees. So we now need to calculate the distance between the point AB and CD again. But it is the same calculation again. So if I just go down, and after all of the calculations, you can see the torque we found out is 3.6 Newton meter, which is exactly the same we are obtaining from the graph. If I go back to the graph, and if I select a random point, this is 3.6 Newton meter. So we have verified the motion analysis results.
Now let's move on to the power versus time graph. Select results and plots. In the Features Manager design tree, in the first section, select Momentum Energy Power. Then select Power Consumption. Here, select the motor from the Motion Analysis tab. Simply hit the tick button. But as I have already plotted the graph, so I will hit the Cancel button. I will jump to the Result folder in the Motion Analysis tab. And at the Power Consumption plot, I will right click and select Show Plot. So this is the power versus time graph. Now on this graph from 0th to the 4th second, only the base motor is rotating. If I go back to the 0th second, you can see that from 0 to the 4th second, only the base motor is rotating. The arm motor is not rotating. So if the arm motor is not rotating, it means that its angular velocity is 0. And the power is torque times angular velocity. So if the angular velocity from 0 to the 4th second is 0, it means that the power will also be 0. Now from 4th to the 5th second, the robotics arm picks up the load. The arm motor rotates 15 degrees upward from the 4th to the 5th second to pick up the load. In this portion of 1 second, the arm motor does have some angular velocity, and that is why the graph is showing power from 4th to the 5th second. Now the power at the 4th second is 0.8 watt, and the power at the 5th second is 0.9 watts, as you can see here. Now the 4th second is when the jaws have just grabbed the load. So it is the case 2 of our hand calculations. And the 5th second, this 5th second is where the robotics arm has lifted up the load. So it is the case 3 of our hand calculations. Now let's jump back to hand calculations in order to validate these power results. But first we need to know what is the angular velocity at the 4th and the 5th second. For this we need to plot the angular velocity graph. So I will cancel the power versus time graph. I will select the results and plots again. And in the Features Manager design tree, I will select Displacement Velocity Acceleration. In the second tab, I will select Angular Velocity. Here I will select Magnitude. And since we want to calculate the angular velocity of the arm, so we need to select any face on the arm. So I will select this face, and then I will select the OK button. But as I have already plotted the graph, so I will simply hit the Cancel button. So I will jump back again to the Results folder in the Motion Analysis tab, and I will right click the angular velocity graph and select Show Plot. Here we are only interested in the 4th and the 5th second. Now here you can see that at both points, at 4th and the 5th second, the angular velocity is 15 degree per second. Now let's jump to the case 2 of our hand calculations. So this is the case 2. I will select the pen tool So here we have the 15 degree per second angular velocity. Now first we need to convert the degree per second into radian per second. Here I have already converted it. So it is equal to 0.261 radian per second. Now simply multiply this value with the torque. It will give us power consumption. So the power we are obtaining after the hand calculation is equal to 0.77 watt, which is approximately equal to 0.8 watts. And the graph obtained from the SolidWorks was showing the exact same power output. I will go back to SolidWorks and I will right click the power consumption graph and I will select show plot. As you can see, at the 4th second, the power output is 0.8 watt. Now repeat the same process for the case 3. I will go to the case 3. This is the case 3. Here again, the angular velocity is 15 degrees, which is equal to 0.261 radian per second. And I will multiply this value with the torque, and we have the power output. Now the power output we are obtaining is 0.934, which is approximately equal to 0.9 watt. And again, it is in line with the SolidWorks motion analysis value. See, at the 5th second, the power output is 0.9 watt. So this was the motion analysis validation. In future, I will upload lectures on structural analysis using ANSYS and will explain what is actually happening behind the simulation results. Because I have observed that most people just perform structural analysis, but they have really no idea of what is actually going on behind the scenes.